All right, so what we're going to talk about today is a brief kind of view from a perspective of a data center company, what is 5G and how we look at the edge. Trishan will introduce Akraino and edge multi-cluster orchestration project that is used as an orchestration layer in this solution. And then we'll look at the application of both to this problem area that we kind of gave it more of a fun name, which comes out to Domino, DevOps multi-domain infrastructure orchestration, right? And we'll show, review the actual blueprint and then show one of the solutions that we actually did for the hackathon, worldwide hackathon that just concluded, ETSI LF-Edge hackathon that our team got the first place, showing how this use case for 5G and MEC federation was realized using this solution. And then, if time permits, I'll tell you who Equinix is, briefly as a largest data center company in the world and interconnection company in the world. So from the 5G and edge perspective, I mean, there are so many kind of discussions about what 5G and what edge is. But as an observation, we're seeing basically the decrease of distance between the user and the application, and then obviously the latency follows. So what's on the on your left-hand side is the centralized model. Oops, what's going on? Thousands, on the order of thousands of kilometers, between the user and the application, and the seconds of latency. And what's in the middle is actually what companies like Equinix did, right? So basically, through peering, through decentralization, improved efficiency of the network. So the network gets flatter. It's actually laws of economics, right? So you need to get rid of the packets as soon as you practically can in order to make it, make the performance better. But where we're going to is this picture on the right, where you have the distances between the user and the application in units of kilometers, and then tens of units of milliseconds. But as an observation, this looks very much like the plain old telephone switch network, right? So the distance between the user and the application was a few kilometers to the central office, right? And then the time to get dial tone was also very fast. So this is kind of like a repeat of what we had. But speaking about the definitions of the edge, I mean, there are many, right? And specifically, if you look at the white papers from LF-Edge, they define edge as in a couple of dimensions, which I don't think they're orthogonal, but positioning, on-prem, provider edge, aggregated edge, and so forth, and then functional, user edge, and provider applications or something like this. But we'll look at this as slightly different because we know that in any part of the networks inside the data centers, we can actually deliver those functions from various locations. So for example, we can deliver a provider edge out of the aggregation location, or we can deliver a user application from a location that is not on the user device, for example, like a virtual set-top box, right? So we're actually looking at it from the latency perspective, of course, right? And then the power capacity and the user capacity, right? So we kind of classify this from the perspective of our view is that we'd rather define this as micro edge, macro edge, and core in terms of those values. And our focus is not necessarily on the far edge or in the cloud, but in the middle. And interestingly enough, from the, I guess, business case and economics perspective, there is a sweet spot, right, where you don't want to disaggregate too much. Like if you start installing servers at all of these cell towers, then it will become expensive, right? So you benefit from a certain degree of aggregation, and basically this type of nomenclature looks good from the perspective of both from the economics and from the manageability of the data center infrastructure and actually network efficiency. Because, for example, if you apply this to a 5G network, the more user plane functions and core capabilities you distribute to the far edge, the more chatter is in the network because of the handovers. Right? Here, you could actually have some balance, right? So we're also looking at, for example, 5G from the perspective of a data center company. 5G is very interesting, but is not as interesting as how we can support the deployment of 5G functions and how, more specifically, we help solve this multidimensional puzzle, right? So we're talking about carriers need to worry about spectrum, fiber, and transport, and then companies like ours provide data centers in different locations, but this is not the answer to the problem yet, right? So we need to solve for interconnection, we need to solve for the distribution of hardware, configuration of that hardware, and then eventually applications and ecosystems. So placing this, solving this manually becomes very, very difficult, right? The next point is that you're talking about the optimality, right? So if we take this infamous use case or infamous scenario that you need 5 milliseconds, for example, of the end-to-end budget from the client to the workload, right? So if you take the best case scenario, the front haul, the lowest uplink and downlink air interface latency, and you take all of that, processing delays roughly, right? So you quickly find out that the remainder of the budget is not that large for your actual application to do application processing. Therefore, a big question here is how do we optimally deploy this infrastructure, right? And how would we do it in a manner that's automated. Another situation is that the complexity increases and increases, right? So for example, if we're talking about network slicing, obviously there are many aspects of network slicing, but as Kalum was speaking to this in the yesterday's session, I believe, we have this kind of vision that the slicing must go on. And it means that the traffic it originates in the mobile domain, but it does not stop there. So it needs to go beyond where the workloads are. So the optimal placement of this functions, including user plane functions, edge computing resources with respect to where the traffic wants to go is critical. And actually, the composition of the slices becomes very critical. So for example, if you wanted a slice that terminates at the local edge compute domain is one thing, but in many cases, applications are hybrid and distributed, meaning that a part of this application can run in one cloud or multiple clouds, and another part could be executing at the edge. So you need to be able to complement the network slicing in the 5G network with something that basically provides continuity in this manner, and it's very difficult to do it manually. So that's sort of a setup for what we're going to be talking next. But before we do this, Trishan, if you want to go ahead and introduce EMCO and Akraino. Thank you.
Great. So as we're kind of leading into sort of the framework and blueprint that we built, but some of the key components that we used with the EMCO project, which is a edge multi-cloud orchestrator, sort of think of it as a lightweight, intent-based orchestrator for your Kubernetes clusters to manage your Kubernetes deployments of the telco use cases. So you can use that, and this is just the high-level architecture here. It's a bit of an eye chart, but we're going to kind of breeze through this quickly and then just talk about the Akraino, which is a set of blueprints. Let's see. Yep. And then let me just show the next one quick here as well. And then Akraino is a collection of blueprints. And you might have heard one of the questions that was raised during the panel this morning was, do you see a place for frameworks and blueprints like this? So Akraino project is a collection of blueprints that addresses several different sort of edge-based use cases. And we're going to go into more detail in the PCEI blueprint, which is where this solution has been built out and tested in. So with that, I think, we'll open this up for more during the Q&A, but with that, I'll let Oleg continue here.
All right, thank you, Trishan. So now we'll look at the, what we call, officially it's called public cloud edge interface, but the name is pretty dry, so we came up with this DevOps multi-domain infrastructure orchestration to really illustrate what we want to do. So this blueprint is part of Akraino, and the subject matter of this blueprint is the orange area on the top, right? But basically what we want to do is to create an orchestrator, right? That's using EMCO and other components. You'll see this later. But basically, that would facilitate the deployment and infrastructure, right, across this multiple domains, including the public cloud and public cloud edge. And you can see these are linked together because what runs at the public cloud edge is often controlled by the core cloud. We want to be able to also introduce, capabilities that are independent of the cloud, where we can orchestrate, multi-access edge compute infrastructure, and interwork with the operator network edge domain. So it's a little bit of an abstract, but all of this needs interconnection, needs data center facility. But we show an example of how this could be tied together using practical production services from public clouds, from interconnection providers and edge cloud providers. How does this relate to 5G? So basically, what we've done working with ARNA networks, we created this orchestrator that has kind of two parts to it, right? It's an infrastructure deployment part where we could operate on this infrastructure, meaning that we could create configurations in the public clouds, create configurations in the interconnection provider domain in the edge cloud, using pretty modern tools like infrastructure as code. And you'll see how we do this. And then once this is created, we then configure this infrastructure by, for example, installing Kubernetes and configuring things like BGP and networking, and then on top of it, deploying applications and functions across this domain. So, for example, we show in our solution, I don't know what's going on here, but we show in our solution, the ability to deploy a Mac application that uses public cloud, and then 5G functions that in a provider domain interconnected all together, and show how application runs end to end. So one word on kind of everybody's talking about APIs and various automation capabilities, but if you think about it, if you're working across multiple domains, like shown here, for example, there is a public cloud domain, there is an interconnection provider domain, there is a edge cloud domain. Everybody has their own APIs, and people who work with APIs probably, my opinion is that the APIs are necessary, but they're not necessarily developers' friend, right? Because you really need to be able to deal with different data representations, data type representations, error condition handling, pagination, all that stuff. And also, if you were to perform a given transaction, for example, create a connection, layer 2 connection, layer 3 connection, using a sequence of API calls, it's going to be multiple API calls, right, that you have to deal with individually. So what we thought, and the other thing is that nobody would ever agree to have a uniform set of APIs everywhere, right? So what we thought about was that infrastructure as code is kind of like a good middle ground that abstracts those APIs and then encapsulates multiple kind of API steps in a transactional, action, right? And then basically creates this capability where what we've done, we've integrated infrastructure as code as a microservice inside the orchestrator. So the Terraform here in this example is not run by a human. Sorry, it's not run by a human. So basically, in this picture, the orchestrator. I don't know what's. Yeah, I think this is a cable connection here. I think the orchestrator runs as a CPU. So basically what it does, it doesn't know what needs to be done in every one of this individual domain. It doesn't understand the structure of the service, component, feature, their parameters. What it knows is that it needs to receive a call from a workflow engine, retrieve the infrastructure as code program, as a CPU does, receive attributes for that program, and run against in a target domain in the steps specified by the workflow. So that's exactly what this kind of orchestrator does in our case. So we created a number of Terraform plans that are parameterized to run against the cloud, against an interconnect provider, against the edge provider, and then build this infrastructure across those domains. Obviously, this implies that the providers of services have to provide the infrastructure as code providers, right? So the software that represents their resources. But since it's pretty much a kind of a de facto situation today, so if you go on Terraform website, you will find various Terraform plans for multiple clouds, multiple providers. So that makes all of those providers more or less uniform, at least represented uniformly with a common language, like Terraform. In the future, this could be Kubernetes operators or something like cross-plane, and that's how we basically operate on this infrastructure. So to show you the practical example of this, this solution for implementing Mac Service Federation, so basically sharing of resources across operators, using infrastructure orchestration as a step, right? And then enabling this IoT application on top was part of the Etsy LF-Edge hackathon that was just completed. And this solution, received the first place and was done by Akraino and Equinix. So our use case was like this. So what you see across the top in orange is this orchestrator that I just described, right? In this orchestration scenario, we have a provider, 5G operator on the left-hand side that basically needed to create a slice from scratch. And that means that they needed to orchestrate bare metal servers, right? Install Kubernetes on those bare metal servers, deploy a 5G control plane and user plane. So that's how we kind of formulated a slice in this case. And then on the right-hand side, we have a MEC provider. So this 5G operator doesn't have any MEC capabilities. On the right-hand side, we have a MEC provider that has a need to deploy their hybrid application. So it runs hybrid because part of it runs in the public cloud, like the backend, the IoT hub in this case. And part of it runs as a cloud-native edge application on edge cloud. That is provided by, basically bare metal resources and Kubernetes installed on top, right? But we needed a private interconnect, right, between the back of this edge cloud and the public cloud, right, using Azure Express Route, but implemented through a interconnection fabric and NFVI service, right? So this solution would basically go out and say, okay, so this MEC operator would access this orchestrator and would start orchestrating the connectivity to the public cloud, bringing up bare metal servers, installing Kubernetes on it, and then proceeding with their infrastructure orchestration. And then in the end, we tied this together because the 5G operator was in Silicon Valley, and then the MEC provider was in Dallas. We tied this together through a production fabric. Sorry. And on top of it, we deploy an end-to-end IoT application. So what I described basically kind of proceeds orchestration proceeds in these stages. So the first is the infrastructure orchestration, as I described, from MEC provider to 5G operator, and then the interconnection in between the two. Then that includes the installation of the Kubernetes cloud infrastructure on bare metal servers. Then we deploy a MEC application on the MEC side and 5G, free 5GC on the 5G side. And then we run the application end to end. So the deployment of free 5GC was kind of also done in a very specific way. We separated out, if you were to take the free 5GC kind of deployments, they're often done all in one. So you get the control plane, user plane, and even the simulation in the same package. So what we've done here, we separated them out. And the idea here is that the UPF itself could be distributed. So in other words, it doesn't have to be co-located near the control plane. And that means that optimality of traffic that I was talking about in the beginning could be achieved by just placing the UPF in the right spot, right? So what we've done basically, once the infrastructure was deployed, this is all described in Helm charts, right? The pods will come up, and there is no difference between deploying this function, right, all this set of functions. The method of deployment is the same as deploying the cloud native application. It's all the same, and that's the beauty of it, right? And then once this is done, we get a full kind of deployment and a full registration of a simulated UE. One other benefit of using free 5GC for testing is that because the UE in this case is implemented is in a container, you could install stuff in the container, and for example, we installed an IoT client, and then that allowed us to pass data across, right? So in the end, basically, we got this picture. This also shows the internal structure of the orchestrator. So as Trishan said, we're using EMCO, like so for the application deployment part. We're using components that came from ONAP, the CDS component that allow us to integrate Terraform as a microservice. Sorry. Ansible as a microservice to be able to basically proceed with this infrastructure orchestration and then use Helm to deploy the application. So this is exactly what we've done in this project. Is basically the architects and developers design their Terraform plans, Ansible playbooks, Helm charts, debug all of this, and this is ready for deployment in this orchestrator as a CPU model. So once the workflow starts, it goes into the Azure cloud, creates the express route, creates private peering, creates a VNet gateway, all of those specifics that come with the public cloud infrastructure. Then we use Equinix Fabric, which provides layer 2 and layer 3 virtual connectivity between infrastructure in the data centers and the clouds. Equinix bare metal to bring up bare metal servers for Mac and 5G, connect them together, install Kubernetes, and then get this Kubernetes cluster information into the orchestrator, and at that point, start deploying the functions and applications. Application is deployed here, right, in green on the edge cloud, and then the 5G functions on the operator cloud, basically telco cloud. And that's really, the end-to-end kind of operation of our solution. I just wanted to touch a little bit why we chose the way, this particular proposition, right? And specifically, an example of Equinix as a data center company. So everybody knows Equinix as a data center provider, co-location provider. But what we're doing is actually providing data centers, of course, but we're linking this together, right, via a private interconnection fabric that is operable on by Terraform, right? So all we've done here is basically accessed, not open, just like in the public cloud is not open source. This is not open source, but we used an open source solution to orchestrate a use case over a production network, right? And this network, effectively, we use two locations, in our case, Silicon Valley and Dallas, but this type of fabric allows us to do it globally if we chose to, right? What is interesting also I'd like to point out here is that the infrastructure that is in place today, right, consists of all these data center layers, right, interconnection, including internet exchanges. Internet exchanges are very important because the optimization of traffic flow from the back of those UPFs to the internet, if they're close to the major peering points, right, is much better than going through multiple IaaSs and things like that. But also, addition of NFVI services and bare metal services integrated with this interconnection fabric is very important. And then exposure of that infrastructure via APIs, Terraform, and portals makes use cases like this possible. So if the public cloud exposes their IaaS and SaaS, that we could operate on using Terraform. Companies like Equinix expose fundamental infrastructure. I mean, we're talking about interconnection, bare metal servers, and the ability to link this all together. This becomes really a very interesting substrate for building, more dynamic type of 5G, for example, solutions, or 5G and Mac solution, or federated solutions that we're showing here. And we've done some math. So this is the US example. If we take all our metros where Equinix has presence, and we basically do a simple model of like 10 millisecond round trip time from those data centers using just the fiber routes, we could, and this holds in Western Europe as well. We basically, cover about 80% of the urban metropolitan population in this circles. But the point is that it doesn't compare, for example, with tier 1 operator coverage. But what it does do is that all of those locations are already interconnected to multiple clouds, and the same location provide bare metal infrastructure and networking capabilities where network providers and cloud providers can meet together, and enterprises. And we can really show the ability to orchestrate this type of capabilities on top of it, right? Which you could also orchestrate and you could remove. You could, deploy, adjust, destroy, and deploy again. What else we do at Equinix? It would sound a little strange, but we actually build a sample 5G, end-to-end 5G network standalone, right? And not for the purposes of building the 5G network, but actually for the purposes of demonstrating how this 5G network could be plugged into what's behind multi-cloud, edge cloud, orchestration capabilities, and how this could be kind of built for the use cases that we're talking about, right? And as a call for collaboration, so we're members of LF Edge, LF Networking, and CNCF. So reach out, and we'll be happy to. We're a neutral party, right? So we'd like to make everybody happy and effective, and make 5G work in this dynamic manner.
So I was rushing through the slide just to keep us on time, but the LF Edge has the Akraino project. The LF Edge and LF Networking are two umbrella organizations. LF Networking has the EMCO project under it, and LF Edge has Akraino, where you'll find this PCEI blueprint in documentation there.
Thank you very much.
Thank you.
I'd be happy to answer any questions.
Yeah, just a quick question, right? In the diagram where you showing this all the workloads, right? In the blueprint, LAN and code. From infrastructure orchestration is clear. You are using these Terraform connectors and others. What approach you are using for the workloads and both the deployment and management, especially day two, right? Because you see in terms of workloads, you show on one extreme the telco 5G, and then obviously there are some routers and IT stuff, and then obviously there will be some edge apps, right? All with different characteristics. So yeah.
Yeah. So great question. So day two, we don't have a solution here for day two yet, right? But what we're doing here is that if you look at this, basically Terraform is responsible for configuring the infrastructure layer, right? But and that configuration includes Kubernetes. But once Kubernetes is in place, then Helm becomes a uniform application deployment mechanism, right? So I touched on this a little bit, but if you look at this application is provided by the public cloud provider, Azure, right? And it consists of a set of Helm charts and CRDs, right? So Helm in this case, all this orchestrator does is basically retrieves the Helm charts, and the Helm charts are run against the Kubernetes cluster. And this results in the deployment of the IoT Edge application. This is an IoT Edge gateway. So this IoT Edge gateway is talking back to the cloud, authenticates to the cloud, uses MQTT to, this is an IoT use case, but this could be an AI or computer vision workload, which is implemented in the cloud native manner. And it basically results in the deployment of the pods that are shown here. The same method, we use the same method, which is Helm, to deploy all of this, right? So all of the control plane boxes in the top box, right? Those are pods, Kubernetes pods, deployed by Helm using Helm charts. Each of them has their own configuration map, how it binds to the, so this box is a VM, right, running on bare metal, and it has interfaces. Then Helm charts have network attachment definitions, and everything kind of comes together basically in one shot, just like that application. So in this case, these pods are control plane, 5G control plane. In this case, the green, like the light green ones, these are application pods. They're just shown differently, but the method of their deployment is absolutely the same. Go ahead.
I saw you use Maltus and Flannel.
Yes.
Was that by choice or by necessity?
So yes and yes, I would say, because we needed a CNI, so this was Flannel, and this is something that worked, right? Maltus we needed because of the multiple interface. So for example, the UPF here has three interfaces that are bound to the pod that performs the GTP encapsulation, decapsulation, all that stuff, processing. It has N3, N4, and N6, right? So that needs multiple interface, and that's where we need Maltus, right? Because we actually, with Maltus, what part of those, I guess the mechanics here is that the Helm charts include things like NADs, network attachment definition. And network attachment definition tells the pod what interfaces it needs to bind to, right? And then the actual logic inside the pod makes use of those interfaces, for their functional manner, right? For their functional purpose. Like the N4 would be like the red color here would be signaling between SMF and UPF. N3, the green line would be GTP traffic, and then yellow is the IP traffic. But that's why you need this. Maltus and Flannel, it's not a simple stack, right? That's for sure. And this solution does not go into acceleration mechanisms, right? So because you also need, in addition to this, Flannel and Malthus or whatever the CNI is, right, the ability to do SRIV, DPDK, maybe SRIV and DPDK, right? And that needs to be kind of baked into the stack, right? We didn't do this here. But it's not getting less complex, it's getting more complex.
So let's take one more question, I think, on
one question. At a very high level, all of this orchestration is for the control plane of 5G, right?
Both control and user plane. So we deployed we used an example where the control plane and user plane and the simulated UE and radio network run basically on the telco cloud, infrastructure provided by someone like Equinix, right? Because Equinix as a data center company not only provides the data centers and the network, but also bare metal, right? Bare metal cloud. So the orchestratable bare metal cloud. But but in principle, this part as is could be run inside the public cloud, right? And then the important part here is that the traffic handling part, like the UPF, like basically where the UPF goes, there 5G traffic goes, right? So 5G traffic doesn't go following the red lines, right? It goes, green and yellow, and it has to be in line with the intended traffic path where it goes to the, where it needs to go, to the public cloud or to the edge compute. So the ability to separate out this user plane function from control plane is very important, and the ability to instantiate this user plane function where it's most optimally placed is critical. And then you can achieve those, targets of, 5 milliseconds, 7 milliseconds, and so forth. That's what we've demonstrated here by separating this out. And all of this is done by manipulating the Helm charts in Kubernetes.
That's where you needed the DPDK in order to have a user plane which is
sufficient.
Yeah,
so we didn't do this in this example, but here you would need to support, like for the IoT, there's no, like you could run it fully in software. If it's like kilobits per second, there's no problem. But if it's really, a traffic demanding application, you actually need something like an acceleration. And for that, I just wanted to say one more thing here. Yeah, so I didn't touch on this in the beginning, but the green slice uses that model that I described, like the green on top, right? So we have the UPF that is shown as a separate function, right? And the core could sit here, right? But this blue and orange slices, we actually worked with Kalum to show another case for the UPF, and that is UPF implemented as part of programmable network fabric. So in this case, here we had to do all that stuff. We had to we have to bring up the bare metal server, install Kubernetes, Malthus, operating system, all that stuff, configure the UPF, and that's a layer cake, and that's the state of the art today. The state of the art tomorrow, specifically for the UPFs that require multi-terabit type of performance, this is implemented in the programmable network fabric. We worked with Kalum here just to show the art of the possible, but these are white box switches with Tofino programmable ASICs, right, that implement the data plane part of the UPF, for which performance is already built in. You don't need to configure DPDK in those. Yeah.
So in general, so it's possible to implement all user plane using kind of the cloud too, actually.
I'm sorry?
You can implement the user plane using the cloud too, in that case.
Layer 2?
You can implement the user plane using the cloud infrastructure.
Yeah,
too.
you could, yeah. The problem is, though, you can implement, let's say, pretend the user plane is here. Because the traffic goes where the user plane is, right? You're going to basically send traffic to the cloud, and it necessarily needs to come out because UPF is not the destination of that traffic. It needs to go to, let's say you implemented it in AWS, and your workload is in Azure. So now you're going to come into AWS, come out of AWS, come into Azure. And when you come out of AWS, you get charged. Yeah. And here, the idea here is that if there is a neutral party that could support this, like this is the case that we're showing, right? Is that not only that this UPF is basically optimally placed, so you don't need to trombone the traffic, right? Secondly, it is, like in this particular case, it is actually part of the interconnection fabric, right? It's not something that you install and configure. It's something that you basically, like you created a virtual router here or a VLAN, you create a UPF, right? That's something, it's a dream, right? But it's something that I think is very promising. Yeah.
We're okay with that all. Great, thank you, everyone.
Thank you.
Thank you.
Sorry about all the display issues. Anyway.